This is a video on titrations, but specifically on whenever you get a titration question which involves some dilutions in a part of it or an extraction. So an extraction is whenever you take a certain volume of liquid out of a larger volume of liquid to use in your titration, for example. And we'll have a kind of look at what that means as we go through the PowerPoint. So if we look just first of all at how we make up a solution which is going to be used in a titration. And the whole thing about titrations is that they have to be extremely accurate. So any solution that is used or made up to be used in a titration has to be very accurately made up. Okay, a really accurate solution, as you should know by now, and one that we know the concentration of very accurately, is called a standard solution. So the first thing that we would do, I've just got a picture here of us taking a precise amount, a precise mass of a solid, and because by having the precise mass we have the precise amount, the precise moles. We might also take a liquid if the substance that we're looking at is in liquid form at room temperature, and we would then dissolve that into a certain volume of water. We usually dissolve it into a minimum amount or a minimum volume of water. Okay, and we always use deionized water when we talk about making up standard solutions or generally doing a titration. We always talk about deionized water to the examiner. Put that into your answer. Never just refer to water in this context. We will then take that and we will put it into a volumetric flask. Now, a volumetric flask is a flask which is designed to measure one volume only. It's not graduated. It has one line on it, one mark on it. Okay, and that the ones that we usually use at A level are probably 250 cubic centimeter volumetric flasks. That gives us a adequate volume for carrying out several titers with. And we pour that, whenever we're telling the examiner this, we pour that through a funnel, okay, just to prevent spillage really more than anything. And then in the next step you can see we rinse out with deionized water the beaker and the funnel both to make sure that every single molecule of our solid or liquid that we started off with has made its way into that funnel. We then use it, and we looked at this a little bit more detail later on, we then use a disposable dropping pipette to bring that liquid in the volumetric flask, the bottom of the meniscus, up to that solitary mark which is on the volumetric flask, usually, as I said earlier, probably up to 250 cubic centimeters. Okay, and that gives us a really accurate way to make up a solution to use in a titration. And we can stand over the concentration of that solution. When you make it up in the volumetric flask, you would then invert it, you turn it upside down and you give it a good shake. Liquids in volumetric flasks don't mix particularly well unless they are actually shook up and inverted properly. Okay, so you've got to turn it upside down basically to get everything to mix well in there. Now, if we then go and have a look at how we might then do the titration. So in the burette here we have our unknown solution of hydrochloric acid. 9 times out of 10 we will have our known standard solution in the burette, but here we have our unknown solution, and then we have, which was made up in our conical flask from the previous slide, our solution of very accurately known concentration, our standard solution in other words. Okay, and you'll carry out your titration. Now, you won't put all 250 cc's from the volumetric flask into the conical flask, of course not. Okay, you will take a pipette and you will pipette out of that volumetric flask. Usually we would take 25 cubic centimeters out of that, but again, read the exam question carefully to make sure that's exactly the volume that you are taking. In this particular one you can actually see we've taken 20 milliliters, 20 cubic centimeters out of it. Okay, that is what we call an extraction. At that point we have 250 cubic centimeters in the volumetric flask and we have taken out of that just 20 cubic centimeters. So we have extracted out of that a 12th and a half, if there's such a word, of the actual volume that's in the volumetric flask, and therefore a 12th and a half of the number of moles that is in it. ask yourself the question, how would the concentration from the volumetric flask to the pipette to the conical flask actually change? And this is the sort of idea of this PowerPoint, is to get the idea of change in concentration as I move from one solution to another, through one piece of glassware to another. How does the concentration change, and how does the number of moles change? Well, have a think about how the concentration changes from the volumetric flask into the conical flask, and hopefully you come up with the answer is that quite simply it does not change. All you're doing is moving solution from one place to another. There's no reason why the concentration would change. You're not adding water to it, you're not taking water away, you're not adding more solute to it, you're not taking solute away, if that's possible. Okay, so and then ask yourself, well, how would the number of moles change? Well, if you look at that conical flask and you have, let's say, X moles of sodium carbonate in it, well, if you take only 20 over 250 of the actual volume with you, well, then you're going to take the same fraction of the moles. So if I have X moles in there, I'm going to divide that, whatever that number of moles is, by 12 and a half, and that will give me the new number of moles, that's called A moles, that I will have in my conical flask for my titration. And that's really important that you're able to work that out. Now we're going to do some exercises later in this PowerPoint if you're a bit confused at the minute as to where I'm getting that 12 and a half from. The 12 and a half is essentially 20 cubic centimeters is 12 and a half times 20 is 250, if that makes sense to you. Okay, but we're going to do some calculations like that as we go through the PowerPoint. So let's have a look at sort of right from start to end here, and we're going to have a look in this schematic here. How does the number of moles change? How does the concentration change as I move from the very start of making up my standard solution here to the very end where I've actually carried out my titration? And what you will do in an exam is generally you will get volumes, concentrations, and therefore number of moles at the very end. And what you will have to do is you'll have to go back from there right the whole way back to the start and work out the original concentration or the original number of moles in a solution that you have been analysing. So I'm just going to work through this sort of very quickly and let you see how and when do the number of moles in a solution change and when does the concentration change, and hopefully you'll be able to follow that. And this is really important, and what I would say to the students whenever I'm doing this is draw a little diagram like this out. Okay, go through the question, find out when they have gone from here up to a volumetric flask, and then when they've taken out of the volumetric flask and gone to there, and draw a little flow diagram as you go along and plot your way through it. How does the concentration change? How does the mole change? How does the volume change? And keep a track of it so that when you're doing their question, don't keep having to refer back to a big block of text. Anyway, let's get started here. So let's say we have a certain volume to begin with. We will have a certain concentration. We will have a certain moles. So let's say we're taking a volume of whatever this is. We don't know what it is. It doesn't really matter. Let's say we're taking 25 cubic centimeters of it, and we're taking a concentration of, let's make a nice round, 1.0. So therefore we have got 0.025 moles of it to begin with, which is 1 multiplied by 25 over 1,000. Okay, I'll just write that up at the top so you remember it. Number of moles, N, equals concentration times volume. Remember the volume is in decimeters cubed. Now, so we've done that. We've dissolved this up in our minimum amount of solvent. We've given it a good wash out. Okay, and then our next thing is we've made that up, okay, from here into our volumetric flask. Okay, we've then topped our volumetric flask up using our deionized water and our pipette, and then finally we've got our filled volumetric flask, which you've inverted, we've shaken, we've made sure everything in there is homogeneous, and we have now got a solution in there that we can now start to analyse. So let's say our volumetric flask, we go to here, our volumetric flask is 250 cubic centimetres. Now what would the concentration be in our volumetric flask? Would it be the same as we started off with, or would it have changed? Well, we've gone from 25 cubic centimetres of it here, and we filled that right up to 250. So the concentration must have been diluted, because remember, all we've added is deionized water, and if you have a concentrated solution right back here and you add deionized water to it, if you're just adding water, you're going to dilute it. Now it has diluted 10 times because I've increased the volume of the water tenfold. So therefore my new concentration here is going to be 0.1. I should have M there, sorry, I've written N. Okay, 0.1 capital M moles per decimeter cubed. Okay, so I have diluted tenfold in that step. Now the number of moles then, well, it remains exactly the same, because all I've done is I've added water from here, this point here, to here. I've just added water, so I can't have changed the number of moles. So the number of moles in here is going to be 0.025. It's exactly the same as it was at the start. Oops, sorry. Okay, so I'm going to let me just tidy this up a little bit. Okay, it's very messy very quickly. Okay, now at this point we are in my volumetric flask there. We were here at 25 cc's there, and now we're going to pipette out of my volumetric flask. Let's say we take 25 cubic centimeters out of it, which is our kind of our standard volume, and we pop that into our conical flask, which we're going to use for the titration. Okay, so our volume here is 25 cubic centimeters. Now as I go from there to there, how's the concentration going to change? You maybe want to pause the video and have a think about that and come back and listen to my answer. Well, the simple fact is that the concentration doesn't change. All I'm doing is moving the solution from one vessel, one container, to another. So there is no way that the concentration could change. Now my moles, I am taking 1/10 of the volume out of that volumetric flask. So if I take 1/10 of the volume, I could only possibly take 1/10 of the moles. So I'm going to take 0.0025 moles and use that for my titration. Now here's the thing that you need to get your head around as an A-level student or a GCSE student. You are going to get from this burette here, you're going to get a volume that was delivered in the titration. You're going to have a concentration of the standard solution that's in the burette, and from that, those two, you can work out using the equation up above the moles of the standard solution that's used to neutralize whatever it happens to be that you have in your conical flask. You will then use that to work out the moles of your substance that you have in the conical flask. Okay, now then, so let's say in this case it was very nicely worked out at being what we happen to have here. Then what you will have to do is you will have to work back from there to there and eventually back to here, and that will allow you then to work out the original concentration of the solution, okay, that you started off with. And that's what you've got to get good at in an exam, is reading the question and checking out, have I just done a dilution, which is what I've done here, or have I done an extraction, which is what I've done here. In a dilution, the number of moles don't change, but the concentration does. In an extraction, the concentration doesn't change, but the number of moles do, by a factor of whatever volume. In this case here, we went 250 to 25, so 1/10 of the moles. Okay, that may not always be as nice around a figure as I've put in there, but the principle will always be exactly the same. In the dilution, I went from 25 to 250. Again, I chose a nice dilution of 10 there for you. The number that you get in an exam may not be a nice round 10, but it shouldn't be too bad. So take a wee minute here to read this question. Okay, I'm gonna go through this. It's pretty simple, but it's a nice little introduction to this topic. So I'm gonna go through it and I'm gonna highlight what I would suggest are the key things. Okay, so what we've said here is we're making up a solution of sulfuric acid. Okay, and we're making it up with 9.8 grams of sulfuric acid okay, and that solution was in 25 cubic centimeters, and then we made it up into a volumetric flask to make up 250 cubic centimeters to carry out our titration with. The simple fact of the matter is that 25 cubic centimeters here would not be enough for us to carry out the titration with, so we need to dilute it to get a large enough volume to carry out a few different titers with. So we've question 1, how many moles of sulfuric acid do you have in the original solution? Well, this time we've got to use two equations. You should be very familiar with both. Number of moles, N, equals mass in grams times the RFM, divided by the RFM. And the second one is number of moles, N again, equals concentration in moles per decimeter cubed times volume, okay, which again, remember from the last slide, was always that. So we've got mass of this, so we've got to use the first equation there, which is 9.8 over the RFM of sulfuric acid is 98. So that comes out. I've designed this to be a nice round number, of course. Then we've said to work out the concentration of the sulfuric acid in the original 25. So now we've got to go to our second equation here, where concentration equals moles, 0.1, divided by the volume. The volume is 25 cubic centimeters, which is 0.025. Okay, so that equals 4 moles per decimeter cubed. Then it asks you what's the number of moles in the diluted 250. Well, all we did there is we went from here to here. Okay, so if you look at our schematic, the number of moles doesn't change. So the number of moles is still going to be 0.1. And then it asks us finally what's the concentration of the sulfuric acid in the 250. Well, the concentration in the 25 was 4. We went up to 250 by just adding deionized water. Okay, so if I do that, I've diluted it tenfold. So hopefully you're with me whenever you recognize the answer is 0.4 moles per decimeter cubed. So we have a little table here, guys. I'm going to talk you through how we do calculate out the numbers on this, okay? And then I will put this table here on the board, which you can work through yourself. And then on the next slide over, whenever you've worked through this particular slide and hopefully filled in all of these blanks, okay, the whole way down, I will put the answers up so you can work through this and then flick on to the next slide, okay, and get the answers. Or check the answers, I should say. Right, so let's have a look at sort of what's going on in here. We have said, or I've said, you have initial volume of a particular solution. So we have 25 cc's is what I've said here. Originally, it was concentration of 0.2 moles per decimeter cubed, and then I've asked you, well, just work out the number of moles, and we just use our equation down here, N equals C times V over 1,000. So the moles in the original one is, it's a bit messy here because we've had to go from one line to the other, but anyway, it is 0.005. I'll just write it up there so you can see it, the value down there. Then what we've said we've done, right, okay, so you've gone from there, so that's we're at this point here. Step 2, if you like, brings us for those first 3 parts there as step 2. Now we've taken this, we've put it into and made it up to the mark in a volumetric flask, okay? So that then, if we go from there to there, this is step up to step 5. So sort of step 3 to step 5, but it's primarily step 5. Okay, now what I've said is we've made it up in this instance to a 250 cubic centimeter volumetric flask. What are the number of moles in the volumetric flask? Well, they don't change because all we've done is add water. We've poured everything from there into that in step 5, so that doesn't change. Okay. What's the dilution factor? Well, we've made it up from 25 cubic centimeters up to 250, so we've diluted tenfold. So therefore the new concentration is the old concentration, which is 0.2 divided by 10, so of course 0.02. Right, so that's that. Okay, let's see then, I'll tidy this up. Right, so now we're going here to here is this part. Okay, we're now pipetting out of the volumetric flask, and we're taking 25 cubic centimeters out of that. So remember, in this question our volumetric flask was 250, and now we've said we're titrating out 25 cubic centimeters. Okay, so what's the new concentration? Well, the concentration doesn't change, because all I'm doing is buretting from one solution, okay, and transferring it into the conical flask. So the concentration from there to there is unchanged. The number of moles changes because I'm pipetting out 25 cc's from a 250 cubic centimeter solution. So the number of moles changes from 5 times 10 to the minus 3, or 0.005, to 5 times 10 to the minus 4. It's a tenth of what I had here, okay? Because if I'm only taking a tenth of the solution, I can only take a tenth of the moles. Right, hopefully you get the concept of that. I'll put up this next slide, which has the big table which you can fill in. The numbers are not quite as nice and round as the numbers that I have there, okay? You can see down at the bottom, even here, I've got 4.3s and 10s and 0.6s and 15s. So the numbers are get a bit nastier, but the principle behind calculating it is exactly the same. So if you want to hit pause now and do that, and then I'll bring up the answers. So there's the answers. Hopefully yours correlate to what I have on the board, and hopefully you can read it okay. I'll leave that up there for a few seconds if you want to hit pause, and then you can check your answers against that. Okay, so we're going to have a look at some past paper questions now, where we now are able to apply the principles that hopefully you have learned. So let's have a look at the first one. This is a fairly straightforward. There's not a whole pile going on in here. Okay, so let's have a look. We have, let me get a different colour pen. Okay, so let's go through the question first of all. You always do this and always pluck out the key things that are happening in this question. Right, so we have a titration was performed to identify X. Okay, now X is X2CO3. The first thing that I said, if I was a student, I would pick out, right, okay, well X must be group 1. Okay, because it's X2CO3, it must have a charge of +1. If it doesn't, whenever you get your answer, you've done something wrong. Okay, we've got a 500 cc solution, and in that it contained 5.2 grams of X2CO3. Okay, and we then titrated against hydrochloric acid, but we only titrated 25 cc's of it. So in other words, whatever volume I had made up originally, I am only going to titrate 1/20th of that volume. Okay, now out of there, that means that the moles, whatever the moles were to begin with, I am only going to have 1/20th of the moles in my titration. The concentration from here to here will be the same. Okay, all I've done is take 25 cc's out of 500 cc's. Okay, so let's have a look at the next slide, because it has the information. Ignore that value there. Okay, so there's key here as well whenever we're going to do our titration. So this gives us an opportunity now to work out the average titers. We have a bit of filling in of a titration table to do here, which will be worth some mark, only worth 1 mark actually. It's quite a lot of work for 1 mark. So here we have 19.3, this is 19.3, this must be 0.0. We have to write everything to the same number of dp. They'll be looking for you to here to write 0 on its own, and they will immediately take your mark off you. Okay, in this one here we have got 19.3 is where we started, and we ended up with a total volume delivered of 18.7. So therefore we have got exactly, if my calculator is right, 38. Now again, they'll be looking for you to write 38 instead of 38.0. And finally here, we started at 10, we ended up at 28.9, so that's 18.9 cc's. I've asked us for our mean. Again, we never use the rough and the mean. Okay, so our mean is simply those two divided by 2, which is of course 18.8. There's no units given here, so I need to put my units in, otherwise I will lose marks. Then we've got to calculate the relative formula mass of the metal and then identify X. So our average titer is 18.9. I'm going to go back to the previous slide where the equation is. So I'm going to fill in the information here. We have average titer 18.9. We have concentration of this at 0.2 molarity. Okay, and we know from up above we use 25 cubic centimeters of my X2CO3 solution. So I have 0.0189, 18.9 divided by 1000 times 0.2 gives me 3.78 times 10 to the minus 3. So the moles of this is 3.78 times 10 to the minus 3 moles of that. The ratio in this equation is 2 to 1, okay, 2 to 1. So I divide that by 2, and that gives me 1.89 times 10 to the minus 3, 1.89 times 10 to the minus 3 moles of X2O3. Now remember, that is in my 25 cc's. Okay. Now, how do I go? Where do I go from there? Well, I'm going to multiply that by 20, because if I multiply that by 20, that tells me that I have, I'll just write that down there, multiply that by 20, I have 0.0378 moles, and that was in my 500 cubic centimeters. Okay. Now the question asked me to work out the RFM. So remember, mass equals moles times RFM. At the minute, I now have, if you look at it, I've now got moles in 500 cc's, but I've also got mass in 500 cc's. So therefore my RFM is going to be mass, which is 5.2, divided by moles, which is 0.0378. So 5.2 divided by the answer gives me 137.5. 137.5. So the RFM of that is 137.5 grams. And now I've got to work out what X is. So this is X2CO3. So if I minus from this 12, okay, plus, which is the carbon here, sorry, plus the 3 oxygens, which are 48, so minus 12 minus 48, that gives me 77.5. Now, remember, that is X2. So if I divide that by 2, that gives me 38.7. If I go to the periodic table and I look for a group 1 metal that is closest to 38.7, I get potassium, which is of course 39. Okay, so you can see there where we had to be on the ball with regards going back from our 25 up to our 500. Right, let's have a look at this one. This time we have a compound called oxalic acid, which is a crystalline solid found in rhubarb. It contains water of crystallization, which is what the examiner is asking us to work out here. It tells us that oxalic acid is very similar to ethanoic acid in the way that it reacts with sodium hydroxide, and then it asks us to write an oxalic acid with sodium hydroxide equation. Now what it tells us up here is important. It tells us up here that oxalic acid is a dicarboxylic acid. That means it has 2 carboxylic acid groups. So therefore, if I know from my organic chemistry that a carboxylic acid group reacts with sodium hydroxide in a 1-to-1 ratio, if something has 2 carboxylic acid groups, therefore it has to react in a 1-to-2 ratio, and it has to lose both its hydrogen ions, which is what ethanoic acid does when it reacts. But this is a dicarboxylic acid, so it's going to react and lose 2. Okay, and I'm going to get that. And remember, every functional group, when it's neutralized, gives 1 water molecule. There's 2 functional groups on here. I'm going to get 2 water molecules. Right, let's have a look at what's going on in the question now. We started off with 1.55 grams of the hydrated oxalic acid, so that's with the water, and that was put into 50 cc's in a beaker. That was then transferred from the 50 and it was made up to 250. Now I've chopped out part of the question here by the looks of it, but what we'll say is that 25 cc's of this was used in the titer. Okay, so and the mean titer is 23.5. So I've got to go from there. So this kind of covers all the bases that we were looking at earlier. We've made a solution up in 50. We've then diluted it up to 250. We've then extracted, okay, from there to there. So from here to here, without getting too messy, is a dilution. From here to here is an extraction. Okay. So let me tidy this up and then we will go about getting the answer to this question. So I said here, sorry, for the titration we're going to use 25 cubic centimeters of that solution. Right, so our sodium hydroxide, okay, let's say, I don't have the concentration, let's say it's 0.1 molarity, I must have chopped that out of the question as well. Anyway, let's say it's 0.1 molarity and our mean titer is 23.5 cc's. So the moles of that is 0.0235 times 0.1, which is going to come out at 0.00235. Okay, now you can use standard form if you want, this purely up to you. The moles then of oxalic acid in the 25 cubic centimeters has got to be half of that because it's a 2:1 ratio. You'd be amazed how many people multiply by 2 by mistake. Please don't do that. Okay, that gives us 1.175 times 10 to the minus 3 moles of the oxalic acid, and remember that's in the 25 cc's. We're going to go up to the 250, and remember going up to the 250 the concentration doesn't change but the number of moles do, okay, because to the 250 all we did was take 25 out of the 250, there was no water involved adding or taking away. Okay, so therefore if we're going up to the 250 cc's, the number of moles in the 250 cc's would simply be that times 10, which is 1.175 times 10 to the minus 2 in 250 cc's. Now, we're now going back to the 50 cc's that we started with. In the 50 cc's, everything that was in the 50, every single mole that was in the 50 was transferred to the volumetric flask. So if that's how many moles I have in the volumetric flask, then that's how many moles I have in the 50 cc's to begin with. Okay? Now, the 50 cc's was made up of 1.55 grams of the hydrated oxalic acid. Okay? So I can now work out the RFM of the oxalic acid. Remember, RFM is equal to mass 1.55 divided by the equivalent moles that was equivalent to, which is, we now know that. So let's do that. And that gives me an answer of 132. So that gives me an answer of 132 grams. That is the hydrated crystals, remember. It tells us that up here. Okay. Now I'm going to take away from that the proportion of this to find out how much water was in it. Alright, so that is 132 minus the 2 hydrogens minus the 2 carbons minus the 4 oxygens tells me that I had, oh, it doesn't tell me anything, I've just typed it in wrong. So let's do it again. 132 minus the 2 hydrogens, the 2 carbons and the 4 oxygens gives me 42. Now the RFM of water is 18, so the 42 divided by our 18 gives me 2.3. Okay, so therefore my X value, my number of moles of water in there must be X equals 2. Okay, you can probably leave it at 2.3 if you wanted. Okay, that would be an average figure of all the X's of all the water crystallizations and all the molecules of oxalic acid. When you're doing an exam, yours will work out better than that. I just made up my mean titer there because I didn't have it from the question. So yours will work out at a pretty perfect round number. Okay, let's have a look at this one here. So we have a sample of hydrated carbonate, similar sort of question to before, and we took 2.79 grams of it. We dissolved that up into 250, okay, and then we took 25 cc's of that. You can hopefully now start to see a kind of a pattern in these questions, guys, which will help you out. So what's the first thing we need here? Well, we don't have the equation, so we've got to get the equation between sodium carbonate and sulfuric acid. Now that's a nice easy one, because you guys as A-level students should know that it is as so. So it's a lovely 1-to-1 ratio. Let's put in the information the examiner gives us underneath it. That's 22.5 is the average titer. We use 25 cc's of this. The concentration of the sulfuric acid is 0.1. Okay, so therefore the moles of this, we just write this up above, number of moles equals concentration times volume. Okay, and our other one, number of moles equals mass in grams divided by the MR. So that is 0.00225, that's the moles of that. Okay, that's just that multiplied by that over 1,000. Now this is a 1-to-1 ratio, so in the 25 cc's of this, I would have 0.00225. Okay, now we're going back up from the 250 back up to the 250 cc's. That's going up by a factor of 10, so that's 0.0225 in my 250 cc's. The 2.79 grams was put into the 250, so therefore I can now work out the RFM of my compound, because I know that this is equal to 2.79 grams, this number of moles here. So therefore I have 2.79 divided by 0.0225. Let me just do that in my calculator. 2.79 divided by 0.0225. That gives me 124. That's a reasonable number. I'm sort of thinking I'm on the right track here with that number. If I take that 124 and I take away just the sodium carbonate part of this to tell me how much water was in it, the sodium carbonate part of that is 106. Okay, so that, taking away my 106, gives me a lovely answer of 18. And I know that the RFM of 18 is, or the RFM of water is 18. So therefore my X value is equal to 1. Nice, easy one there, I think. Okay, right. Let's have a look at this one here. Alright, so this time we've got the percentage of water crystallization of a sample can be determined. We've got 5.72 grams of this. Okay, now this is actually very, very, very similar, isn't it, to the one that we did, yeah, back here where it was 5.2, so I suspect that this is probably going to be something very similar. Anyway, we've sodium carbonate, hydrated sodium carbonate, so just remind yourself of the formula of that. You'd be amazed how many people do this and write the formula of sodium carbonate as that, and immediately they're going wrong, end up tying themselves in knots. So we took that and we put that into 500 cc's, and then it tells us here we took 25 cc samples out of that to titrate against our hydrochloric acid. And now again, we don't have an equation, so it's really important that you are able to write your equations. Okay, and you know, or at least you know, the ratio of some of these acids with some of these common bases and alkalis. Okay, so this one is as so, and the important thing here is we know the ratio is 2-to-1. Okay, we haven't been given the mean titer value. They're going to make us get it here. Okay, the rough, we're going to have to fill this in, so it's 20.5, but again we don't take the rough into account for our accurate, or sorry, for our mean, I should say. So that's divided by 20.5. I know that's dead easy, but I like to do it in the calculator just to be 100% sure. Okay, I'm not going to do that one on my calculator. Okay, so those are my two accurates. The average therefore is 20.0 cm cubed here. I know that volume is that, so therefore the number of moles of this is 0.2 multiplied by 0.02, so that's 0.002 is the moles of hydrochloric acid. The ratio is 2 back to 1, so it is 0.001 moles, and remember that's in 25 cc's. My 25 cc's came from 500. That is a factor of 20 up. So I take my 0.001 and I'm multiplying that by 20 to work out. So that gives me 0.02 moles. Remember, that's in my 500 cc's. That 500 cc's was made up of 5.72 grams. So that number of moles is equal to 5.72 grams. I do my 5.72 mass divided by number of moles, 0.02. 5.72 divided by the answer gives me 286. It's a much bigger number this time actually. So that gives me 286. That's the RFM. Okay, from that I take away the sodium carbonate part of the hydrated crystal. So remember, the whole crystal is Na2CO3.X H2O. Okay, the whole thing now I know is 286. So I'm going to take 286 minus the 106. Okay, it gives me 180 grams of water, and I know I'm on the right track because that's a nice round number. 180 divided by the RFM of water means it's 10. So my X value in this particular instance is going to be 10. I've calculated X as 10. Okay, I think this is the last one. I hope it's the last one. Right, so a 1 gram sample of fertilizer containing ammonium sulfate was heated with 100 cc's of 0.1 molar sodium hydroxide. Okay, heating was continued until all the ammonia was driven off and the remaining solution was made up to 250 cc's. Okay, oh, this is a back titration. This is difficult. I'll probably, if I was you, I'd pause the video now. Back titrations aren't on the AS spec, but those of you who are really confident about what we're doing now should be able to have a go at this. If you're looking at it and you're really struggling, we'll just play the video and I'll talk you through it here. Okay, but this is back titration. It used to be on the AS spec, not on it anymore. Anyway, so basically what they've said here is this is in excess. Okay, and all the reaction is carried out, and then at the end, whenever the reaction is over, this excess, the unreacted sodium hydroxide in there, is reacted with hydrochloric acid. And we only use this titration to then work out how much sodium hydroxide is in here left over, okay? And then we can work out how much sodium hydroxide actually did react. Anyway, let's talk ourselves through it. So let's put in what we know. We've 1 gram of this fertilizer containing ammonium sulfate was heated with 100 cc's of that, and that was 0.1 molarity, okay? And it tells us there it's in excess, okay? The heating solution continued until all the ammonia was driven off, and the remaining, everything that was left over, was made up to 250 cc's in a volumetric flask. We then took out of that solution 25 cc's and we titrated that against hydrochloric acid. So this 25 cc's contains unreacted sodium hydroxide. So that sodium hydroxide was titrated against hydrochloric acid, and again that, hopefully you know, is a 1-to-1 ratio. Okay, a very common acid-base reaction. And from there we had 0.04 molarity HCl, and the average titer was 23.5 cc's. So the amount of HCl that was used was 0.04 times 0.0235, and that gives me number of moles of hydrochloric acid used, 9.4 times 10 to the minus 4. Again, standard form is fine. It's a 1-to-1 ratio, so therefore I have 9.4 times 10 to the minus 4 moles of sodium hydroxide left over after the reaction. Now, at the start of the reaction I had 0.1 times 0.1, so in other words I had moles of sodium hydroxide here, I had 0.01. Okay, that's how many moles I had to begin with. This is how many moles I have that have not reacted, but I need to be careful because that is how many moles that are not reacted in 25 cc's. Yeah, that came from this 250 cc's that was made up. So therefore my sodium hydroxide that is left over unreacted but in the 250 cc's is going to be 9.41 times 10 to the minus 3. It's this times 10. The moles of sodium hydroxide that I started with was 0.01. This is what's left. I can now work out how many moles of sodium hydroxide actually did react. So that is 0.01 minus 9.41 times 10 to the minus 3. So the moles of sodium hydroxide that actually did react is 5.9 times 10 to the minus 4. That's how many moles of NaOH actually did take part in the reaction. Okay, now the ratio of sodium hydroxide, okay, let me just tidy this up a little bit up here because I'm going to work up around here now. Okay, so if we just pop in the moles of sodium hydroxide that reacted, now I have it at 5.9 times 10 to the minus 4. That is a 2:1 ratio. So if I divide that by 2, that tells me how many moles of ammonium sulfate were in my fertilizer. That gives me 2.95 times 10 to the minus 4. That's how many moles of ammonium sulfate were in my 1 gram. Now I can convert that into a mass of ammonium sulfate by multiplying it by the MR of ammonium sulfate. Let me work out what that is. So that is 36 plus 32 plus 64. It's 132 if I've punched in the buttons right in my calculator. If I multiply that, sorry, I'll just put that on there. That's 134 is the RFM of that. If I take my RFM and I multiply it by my moles, so multiply that by 2.95 times 10 to the minus 4, that gives me 0.03894 grams of ammonium sulfate in my 1 gram of my fertilizer. So therefore, to work out the percentage of ammonium sulfate in my fertilizer, I've got to do 0.03894 divided by 1 times 100, okay, is, I guess 3%, isn't it? Yeah, 3.8. So it's 3.894% of ammonium sulfate in my fertilizer. Okay guys, that's all I'm doing. Hopefully you've got the gist of that now. There's loads and loads of titration questions that you can have a go with, similar sort of concepts going on, but hopefully that helps you